think we're about to go live here. Just going to hit the refresh button to check that we're live, because I think we are. And today's video is about multiprocessing. So in the meantime, while I'm checking it's live, I'm just going to zoom in a tiny bit. And I'm just going to go to the actual live cast, and I'll do a share as well. So I'll share this out to Twitter, which is x.com. If anyone wants to join, so I'm going to hit the post button. If anyone wants to join, you're welcome to join there on Twitter. And yeah, I think we're going to crack on basically. So this particular piece of code is inspired by this question, which is over here, and I'll zoom in on the actual question. But basically somebody's asked, I've seen these types of questions quite a few times before on Stack Overflow. So concurrent futures used, but only one core is active. I'm trying to understand the concurrent futures, so I wanted to create a small example. So in this particular example, the numbers from 1 to 10 to the power of 7 shall be summed up, and I want to use 4 cores, so I created 4 lists, and these are the 4 lists here. This one here, this one here, this one here, and this one here. Okay, nice and cute. But when I run my script and check the system monitor, okay, he's using Linux here, Linux Mint 21. I do actually have that, but I'm actually using Windows. And you know, Windows, you do it in a slightly different way, but you've got a resource monitor over here. Now my resource monitor is pretty much all full up, but that's because I'm streaming. But what he's really referring to is, you know, and again, like, it depends on how many processors you've got, but here on this particular PC there's 4 processors: CPU 0, 1, 2, and CPU number 3, and then we've got a total 1 at the top as well. I think, I'm not even sure that's the total, and I don't even know what the usage is, but basically we've got these four cores over here on this particular one. But you might have 16 cores or 20 cores or whatever, how many cores that you have. So that's that. And actually, when I do run this code, although it won't show on the cores, we should see one of these basically jump up. So if you're using like 1 core, it should jump up. If you're using 2 cores, it should jump up. So if you allocate it to all 4 cores should be put to work. And that's kind of like the whole purpose of this, which is basically something like, you know, we run a process over here. So we've got this process, and then we allocate it. So if we just do single threading with nothing, it will just go to, like, it'll be assigned to 1 core, like CPU, that CPU over there, like CPU 0, or it might be assigned to CPU 2, but whatever it is, it should be assigned to a CPU, in theory, that is. And if you're doing multiple processing, you can assign it to multiple cores. So you can go, like, let's, you know, assign it to, you know, these 2 cores over here. And if we're using these 2 cores, it should conceptually at least take half the amount of time. So that's pretty much the ethos of concurrent futures or multiprocessing. I'm going to show both. But the question was initially asked with concurrent futures, and here he's got this import concurrent futures, and he tried to do it. And the question is when I run my scripts and check system monitor, I see that only 1 core is used. Shouldn't it be 4? So, you know, we go, you know, this is the actual script itself. I haven't actually run this particular test script, but somebody did post, and then probably I should run this test script. Maybe I will at the end or something, but somebody did post a comment as the first comment, which is this one here. This is how you do it with concurrent futures. So basically it looks like he's got this range, the same range, and he splits it into 4 lists over here. And then he goes along and does the computation of them. And what he's saying here is, with a concurrent modulo list in question is executed 4 times in sequence, and okay, the compute sum. So basically he does this bit here, which is the process pool executor as executor, and then so with it, I guess he goes through and runs each one like that. And my question was, and he gets the output over here. And my question was actually, so I've actually posted this question, which is over here. Why not use the multiprocessing module, which would have been my suggestion. Like, that's what I was going to use, but I've seen that this guy's using concurrent futures, and it looks quite cute and a small piece of code. So anyway, I went along and I actually thought, you know what, I'm going to do this method anyway, the multi-processing method, and then I decided afterwards I'll compare them side by side. So that's basically what I'm going to do. In fact, I'm going to compare 3 methods side by side. So this is the actual code itself, and I've done a bit of work on it to get it in the right shape. So down at the bottom, we've got our standard if dunder name dunder equals double underscore main double underscore pattern here, the main entry point of the code, and that jumps us all the way back to our main module. So if I go to definition, it will jump us back to the top. And in the top, we've got 3 particular things that we're doing. The first one is no multi-processing. So if I jump to that one, go to definition, this is a really simple one, which is basically simple single thread process, right? All it does here is ignore the time at the moment, but we set a number, so we go 10 to the 7, then we define an array which contains all of these numbers from 1 to 10 to the 7, and then we do a total, which is just a sum array, and our sum array is this little function just above it here, which does the sum of the array, and so it adds them all up, and then it prints out the actual total. Now I've inputted a time bit here, so I start a timer and I end a timer. And the reason why I do that, and I do this for each function, is to show how long it actually took to run this function. So we're calling this the no multi-processing function. This is single-threaded. So how long will it take to run a single-threaded function? So that's our first function, and that's up at the top in the main module. And we called it no multi-processing, and now it just says simple single-thread process. The next one I've called multi-proppy. Let's go to it, go to definition. And again, I've started the t equals 0, and I've done this same list over here, or this array, not a list, because it's a NumPy array. So I've done this array, and I split the array into 4 bits. And I was like, because I was doing that, I was like, well, how long does it take to actually do the split of the array for a start? Because that's going to cost me some time. And I don't want to confuse the splitting of the array time cost with the actual time cost of doing the multi-processing as it was. So not only do I have a T0 and a T1, so that's a split time, and I could actually call it the multi-property split time. Copy that, because just how long it takes to split this thing up. But we've actually got the multi-property calculation time, which is just T2 minus T1. So we do another time calculation for this period. I'll draw it in red actually over here. So we're basically computing this little block of code over here. So it's kind of like how long does it take to, not that bit over there, so let me hit an undo. How long does it take us, really I should have done the T1 over here, I guess, whatever, we've got a print statement thrown in. How long does it take us to run this block of code over here, basically? That's kind of like what we want to know, because that is effectively we're splitting it into 4 processes. So this should be going out to processor number 1, or in our case processor 0, because the first one is 0. Then the next one over here is going out to processor number 1. Then this one's going out to processor number 2. And finally this one's going out to processor number 3. And if it's working in the right way, we're splitting the array into 4 sections, so each one now has to do. So if this was our original array, which is that long, if we split it into 4, which is split into half and half again, each one of these only has to be a tiny amount. So each processor now just does a much smaller amount of work. So instead of allocating one big block, this whole block over here all to one of these processors and waiting the entire length of time, we should be able to split it into 4 and allocate it to 4 processors, and then do the combination of the sum of the 4 processors afterwards and return it, and it should be a quarter of the time. So that's what that basically is. And so that's our multi-proper one, and this is, I'll call it the multiprocessing method. Okay, so that's our second method over there. And so now when we hover over it, it says the multiprocessing method, and our fine one is conky futures, which is the concurrent futures, which is using this process pool executor over here, and it's doing the similar thing, which is breaking the process down into like it's 4 pieces. But what we're interested in, so it's got proc equals 4, and I presume that is allocating to the 4 processes here, and it's going to this executor process over there, and it's going to map it and split it into 4. So it's doing the same. It should be in theory doing the same thing, i.e. allocating. This should be doing an allocation 1, 2, 3, and 4 to 4 different processors. So we've got processor 0, processor number 1, processor number 2, and processor number 3. Should be doing some kind of allocation like this. At least that's what should happen under the hood. So we've got all of that going, and I'm just going to give that a label. You know, some of these functions have a support function in here. So this one's got the compute sum, which calls this function up here. So it's doing a map of this compute sum, and the compute sum is just, it just looks like, well, what's it doing? It's adding all the things to a list. Basically, it's making this big list, and then it's returning the sum of the list. So, and it's doing it for one in every 4 items there. So, and this might be a reason why what we're going to observe is at different times, because it's operating on a list and the other one down below is operating on a numpy array. I reckon that might be a reason why this concurrent futures is slower. But let's just go along and do this anyway. So this is the concurrent futures method. Right, and I've actually called them this as well in the print statement, so we can see the actual calculation times. So now if I hover over it, we've got the concurrent futures method. So we've got 3 methods here. Simple single-threaded process, a multi-processing method, and our concurrent futures method. So these are our trio of methods over there. And I'll just do another share on the live stream. So I'm just going to share again and hit Twitter. Share it second time out so that people get a chance to come in. If you are watching this, you're more than welcome to put comments in the comment section as well. And I'll just hit a little test on here, so test just to make sure that comments do come in, so I can see comments coming in. So this is our multi-processing, and everything's now in place. And I'm going to zoom out because I've got this little mini map over here, but that's probably not good enough. But just so that we can see what it actually looks like, so control minus a few times. And I'll even, for the sake of it, I'll put hashes over here. I don't normally do this, but this is the concurrent futures section. So I'll do something like this. I'm not a fan of doing this, although I used to many years ago. But this is the multi. You know, I'm going to steal some words here. Why not copy and paste what you can? This is the multi-processing section, and finally we can see where the last section comes in. So let's copy that down here, and this is what I've called no multi-processing, so that I'm going to call it that. So hopefully it's a little bit clearer to see where the 3 sections are in this. I don't normally do that, but you know, we can see where they are now. So, and this sum array is just again just another support function that gets called by multi-processing. In fact, I've used this twice. This sum array gets called from this no multi-processing, the single-threaded process as well. So we've got our 3 processes there, and I will even label them if I can zoom out a tiny bit. It's going to get small on the zoom out, but there we go. You know, if I do a labeling here, this is method 1 right there. This is method number 2 over here in the middle. And finally, this is method number 3. Now, method number 3, for a start, is the cleanest and shortest, because all it is basically a sum of an array. It doesn't do any splitting of anything. It doesn't do any allocating of processes to any processors. So it doesn't do any of that at all. All it does is literally just allocate to one process. So if I was to bring this in over here, this is my cause again. Method number 3 is just literally, it's just going, you know, I'm just doing that over here. Just go to this processor and allocate all of my time to that. Whereas the other two are, you know, sort of like going out, you know, in 4 different directions. 1, 2, 3, 4 arrows coming out, 4 lines coming out. And the same for this one. It's going like, let's do 4 processes and allocate to 4 processors, right? And that costs us an overhead in terms of we have to split up the arrays and organize our stuff, but then it should be a cost saving afterwards. So what we're going to observe though is that there's no cost saving, and you know, I'll go through the reason why lightly, but I just kind of like wanted to run them all just so that we can see where they are. So I'm going to do a zoom in again so that we can actually see when I run it in the terminal, and I actually hit clear here before so that the terminal's nice and clear. So let me just do a Control Plus to zoom in a few times. And all we're going to do is, at the end of each of these modules, is get the actual print statement that comes out. So multi-property split time and so forth. So we're going to get each one of these sequentially. So we'll get the single-threaded one, then we'll get the multi-processing one, then we're going to do the concurrent futures. And we're doing them all to 10 to the power of 7. Now, I could have made a global outside, which I possibly should have, you know, so that I just have to, if I wanted to change this number once, I could, but you know, it doesn't matter. I have to change it 3 times for the 3 different methods, but I've done that anyway. So we've got 10 to the 7 on the top method, we've got 10 to the 7 on the second method that's over here, and finally we've got 10 to the 7 on the third method. And actually over here, it's, I think the top one, oh no, I did remove the plus 1 because it was written 10 to the 7 plus 1. But 10 to the 7 plus 1, for the purpose of our calculations, is pretty much the same as 10 to the 7, 10 to the power 7, right? We don't need to add the extra 1 on there. It won't take that long for the purpose of computational time. So I'm going to hit F5 to run this now. And we're going to see it go. And if we did have our processes, if I wasn't running this resource monitor over here, I mean, you can see it go up to the top, but really, like, it's already like maximized because I've got the video streaming on here. So I'm presuming that the video streaming is using a large part of it. But if the video streaming wasn't using a large part of it, you should see them jump. But what we actually notice here, and this is the interesting thing, is if I go over here, we've got the no multi-processing calculation time is 0.072 of a second, right? And then I've split the so that's a single thread over here. It's fast. And what we notice is the multi-processing time not only has it actually cost us in terms of time, it's cost 0.1 of a second. That's already, it's longer, it's taken longer to split the array than it has to do the sum of the array. So that's the first thing. But second of all, because I split this into 2 parts, it's really weird because I'd have expected this, at least that was the, I'm going to call it, this bit here is the overhead over here, right? Right, because that's the cost of splitting it. So that's the overhead. Right, but this bit over here is actually the gain, because this is the computational time, and this should actually, I'd have expected this to be roughly a quarter of the time of this, so a fraction of a second. Now, you do have to join them up at the end, because basically what happens if you've got this thing, you split it up into its 4 bits, you do your 4 computations like this. So there's your 4 computations over here. And then you have to effectively rejoin them. You're summing them all back up at the end over here like this. That's effectively what this process is doing. So that's kind of like your final output. Now, what this is telling us, so I'm going to say this is kind of like, this in theory is our gain. So I'm writing this in like rubbish little font, gain, there we go. But what we notice is that this has taken 5 seconds basically. And even worse than that, is when I go over here and look at the concurrent futures calculation time, this one is a whopping 12 seconds. Now, I know it sort of like combines the two, and also argument, like for the purpose of argument, this one, because you have to compare them on a like-by-like basis, and I didn't really, because I took the code. This code was actually taken from this answer up here, and this answer up here actually uses a list, and I can like spot this list here. In a minute I spot a list, I know that it's going to be slower than a NumPy array, so maybe I could turn it into a NumPy array. So, you know, I might take this with a bit of a pinch of salt over here because it's got a list. Lists are automatically slower. The way they work is just not as efficient as NumPy arrays, so straight away you should be doing that. So I take that with a bit of a pinch of salt, but the concurrent futures calculation is also slower over here. So the question is why, really? And I actually don't fully know the answer. Well, I partly know the answer. I can partly explain it. But one thing about this, and I've seen this a lot, is, you know, people ask questions quite a lot on here, like, so like, you know, I want to split this up into 4 cores for processing, you know, and what I notice is that this takes longer. Now, I guess there's no, you know, one thing that I'm going to say straight off the bat is there any particular gain? Like, I would expect this to be a loss straight away. But you have to sort of like do a setup, if you imagine, of your NumPy array before you do the calculation, and that's got a cost in itself. Now, maybe if this was like a 30-second process or something much larger, so if you're doing some AI and, you know, some tensor algebra or something, maybe you're going to start to get the gain over here. But for standard and for most Python, and I barely ever, like, I'm not even sure if I really have used multiprocessing. Maybe I've used it under the hood, or I've used it on 1 or 2 occasions. But basically, that's one massive reason why for huge amounts of Python code, most Python codes, you won't use multiprocessing at all, because the overhead and the costs and the splitting up of it actually doesn't save you any time pretty much whatsoever. And it's really only reserved for kind of like very large processes, you know, I don't know, maybe even where it's going to take like, you know, minutes, hours, days or something for your calculation, where you're going to start to see a gain and basically you're forced into doing it. So if I've got something that's taking, you know, a second, maybe even 10 seconds here, you could argue, but if I've got something that's taking a second or 5 seconds or, you know, 20 seconds, I probably won't be doing the multi-processing, and that's a very common mistake that people make. And the other one is quite often they confuse it with threading, and that's totally different, because threading is for input and output, and async I/O as well, which is a threading type thing. That's for inputs and outputs, and basically most of the time cost in threading is waiting for the input and output, so the latency in the actual system, rather than the processing time. So that's pretty much it. What we did, so what we've actually discovered accidentally, and I did post this in the actual answer itself. But one thing is, so I tried to take these all to 10 to the power of 9 to see if that would make a difference. But taking this one to 10 to the power of 9 just like literally hung the computer. So I'm not even going to attempt to do that. I could actually attempt to do it on the other two. So I'm going to comment out the conky futures now, and I've got the multi-processing, so I've got the single thread, which is the no multi-processing, and then I've got the multi-processing over here, and I'm just going to change this to a 10 to the 9 over here, and so I'm not going to touch the, so that's our simple sum there. Yeah, that's the only bit that I need to do there. And yeah, because this compute sum, this 10 to the 9 goes, this 10 to the 9 here, which goes into the, which is in the compute sum. I need to scroll a tiny bit down on that. So one more down, there we go. I have to do that again. This compute sum, which has a 10 to the 9 over here, it feeds into this compute over here. So that's what would have happened. if I was using the concurrent futures, but I'm not going to touch that one. We're not touching that anyway. But on the multi-processing one, I'm going to increase that one to 10 to the 9. So I'm not actually touching this concurrent futures one. I'll leave it. We're not touching because it's literally going to just blow the computer up. It will take too long. But then I'm going to compare it to this single threaded one. So let's take that one to 10 to the 9. And if we do these run again, so I'm going to do an F5 to rerun it a second time. So now we're only going to get 2 answers spat out. It's going to take a bit longer because we've done 2 orders of magnitude more. We see that this one here now takes 3.5 seconds. So that's the first one. And I'm really hanging around waiting for the multi-properly split time. And we've got the split time. It took 1.5 seconds, unbelievably, to split the array. That seems a little bit odd. And I mean, look at that. I mean, like, whoa, it's taken 18 seconds. Now, again, straight off the bat, I'm going to say something, which is that this one here has gone scientific mode. And if I look here, and this is probably the reason why. So this goes more into like really, really being accurate about how one uses Python. I don't know if this is split this, and it indicates to me it's using floating point numbers. Now, if it is, the NumPy array, instead of being an array of integers, the NumPy array when splitting up, and I don't know if that's the case or not, but that's integers, so they're all kind of like short things over here because an integer is shorter. If in the split, when I thought I was splitting it into 4, so 1, I haven't got 4 splits here, 2, because I haven't drawn it nicely, 3 and 4 over here. If these are turned into floats, these are actually wider, so there's more like data literally going into these 4 things over here. So they're all going to take longer to read. They're occupying more memory. And so what we've got is this slim, thin one, and I could have inadvertently, while doing multi-processing, so it cost myself extra by increasing this to like an integer might only occupy, I don't know what it is, unsigned into like 16 bytes of memory over here. So the width of any one of these is 16 bytes of memory, whereas a float might be like 64, right? So I've just cost myself inadvertently, accidentally, a huge amount of time by doing the multi-processing because of something that I didn't know. Now, I just wonder if, because one of the things that I did was, if that is the case, and I did it in the sum array here, which is this unsigned int, and I wonder if I can just to be on the safe side, and I don't know if this will make a difference or not, but when we split it into our 4 arrays, I wonder if, first of all, if the array dot split, what else can you put in there? I don't know if I can put a D type in here. I don't know if it will allow that or not, or throw an error message and give me back 4 of these, because maybe it will. I literally don't know. F5, let's see what gets returned back. Really, it doesn't look like it's thrown. Oh, actually, I won't know if it's thrown an error yet because it's done the first one. It has. Oh yeah, it has thrown an error. It hasn't. Didn't like that. So it wasn't allowed to do that. So that was still the 3 seconds that it took. Next, what I'm going to do is actually this array split. Look, is it returning back a list, but of an ND array? Let's have a look. I did this because I could actually inspect this, which is I'm just going to do a print of array 1. I just want to see what's in there. So I can do this, and then I'm going to do a I'm going to hit a return early, right? There we go. So it's not actually going to run this piece of code now. It's just going to return early. I'm going to try and match them up basically. So let's just do that. Just want to see what array 1 actually looks like. So what are we getting back from this NP array? Because I would have expected to get back another NumPy array. And I do actually. I get another NumPy array of integers. Because if it was float, it'd say 1.0, 2.0, 3.0. And it hasn't done that. So it wasn't even that. So I'm a bit unsure as to where the extra. I know that the extra time cost is there because we're literally measuring it. But I'm a bit unsure as to where the extra time cost would have come about. But there's a huge time differential in actually doing this. So I can't enhance over there because this here is an array of integers. These are all arrays of integers. And this sum array is the same sum array function because, and both of these are actually using this sum array function. The sum array function is actually quite small anyway. So where is the cost of this? I guess potentially I could time each one of these. Because what I do know is the time is between these two. This print statement won't be the cause of that long a time delay. So I'm trying to understand where. What we can actually do is, maybe I will do this. I wonder if within the with statement you can put something like a T3, but that should be allocating them all simultaneously. So time. The funny thing is that these should all happen because this should run asynchronously. So I'll do that over there, and I'm going to do some more split time. So I'll call it the multi-property split time. There we go. So I'll take that out, paste that there. Which is going to be T3 minus T1, okay, and I'll put another one in here, copy that, and I'll paste that over here, and this will be T4 over there, and that will therefore be T4 minus T3 over there, to T3. Now, this is kind of like inside the with statement. I wonder if it's going to work like this. So let's just have a look anyway, see what happens. We're going to get 2 extra split times in our split time thing before we get our multi-property calc time. So that's taken our standard 3 to 4 seconds as expected. Now, we do see like that's taken. So to get to the first split, i.e. split the array into 4 segments, costs 2 seconds. To get to the second split costs a fraction of a second. To get to the third split costs 2 seconds. And then we've got 19 seconds. I'm wondering where the 19 seconds has come about from. That's an interesting one. So I'll go here and then do this one over there, which is the T5 process. Although I think this is actually materializing now. So now I'm going to have to do a T5 minus T4, and on the final one we've got this bit, and it looks like my cost is actually going to come. I'm just assuming here that the cost is going to come from the time from the r.get thing over here. r.get for r. Surely it'll be quicker just to do the sums of all of them for r in all of that. I wonder if that's a cost, but we'll see that. So I've done a T4 there, and right, T3, T4, T5, and into the T6 there, sorry, T6, because that's going to be the last one, which is T6 minus T5 over there. So that's how long each little section has each one of these res pools has taken us to do. And if I could like put a space between them, we can see each one of these res pools. So there we go, like sequentially. That's our first one, that's our second, that's our third, that's our fourth, and then our sums. So we'll see it hang basically after sums. And then we're going to get our T2 finally, which is the difference between all of them. Okay, let's just do, we no longer have to call this, well, we can call it T2, but we're not going to subtract from T1. We're going to go from T6. So we're basically jumping. We just want to see how long it takes to get from here to here. Basically, this is T2 minus T6. But effectively, what we're saying is how long does it take to compute this bit over here. So, and the sum of all of those components is going to be, it should be the whole 19 seconds that we observed over here. So let's just run that. So we'll just hit delete on that, and we'll hit an F5 to rerun it again. So now we're going to get a whole bunch of split times. And we're not going to get, we still will get a count time at the end actually as well. Okay, now our count time is we need to get a bunch of split times. So we do, and in fact, interesting, because we get this gain like 0.001, 0.000. That's taken 2, so that's still taking the bulk of the load by the looks of it. So it's almost like you've got no gain, as in the single thread was as fast. This has taken most of the single thread, but actually all of the time taken. So that's an interesting one. Is in this bit here, which is the r.get for r in res 1, res 2, res 3, res 4. So I'm just wondering if it's easier just to do total equals r dot or res 1 dot get. And this is the cost, is res1.get plus res2.get. I can't see why that list comprehension would be materially slower than adding up 4 res.gets. So that'd be res3.get. And finally, res4.get. That would be the equivalent of what we are doing over here, but there's going to be no gain. In fact, the list comprehension should be, list comprehensions I think in general are faster, so but that shouldn't cost us 17 seconds. So this r.get it's like it's going to a processor and it's costing us quite a few seconds to collect the answer, but that's probably why. Or at least I wasn't expecting that. I was expecting there to be basically an overhead on entry. So, and again, let's scroll over here. Our entry points basically is, if I can get there, I'll squeeze it all in there. Yeah. Our entry point is here, which is basically we know automatically we're costing ourselves time, right? That's a cost because we're breaking up the array. Right, so that's our entry. Right, so that's our enter cost over here. But this is our gain because we've split it into 4 bits. Although we've seen at the bottom that really nearly all of the stuff I think went into one of these. Like, so basically the bulk of the work was done here. This did most of the work, right? And then these guys here did a puny amount of work. Right. In fact, one of them was like 0.00 seconds. They did no work. So, like this did like, I don't know, like 90% of the work. This did like, 5% of the work. And this did like, it wasn't even 5. It was like maybe like 8% of the work or something. This did like 2% of the work, and this did like a fraction basically. This is basically nothing, 0, big fat 0. So that's kind of like, so the multiprocessing didn't work sort of like in the efficient way that we wanted to. So that was kind of like one, but maybe that's because you have to take it to a higher number. So I can try and take it to a higher number, but really, the cost was getting the data back. This was a huge cost to us. Wasn't expecting that, which is the exit. So in the multi-process, we don't just have an enter, but we actually have an exit here. We can see this, irrespective of what anyone tells anyone on, how multi-processing works. We can see that with an entry cost. We can see that the processing wasn't allocated the way that we wanted it to be, because we could literally measure the times of these pieces. And then finally we could see that the exit had a huge amount of cost. That was like 17 seconds, getting these 4 bits back from the different cores effectively, and adding them up. I don't know, that's what it was. So I wonder if I try and do it again for a bigger number, if this basically stays at 17 seconds, or does this get even heinously larger? So I'm going to increase it by another order of magnitude over there. So we'll go from 10 to the 9. Should we just go 10 to the 10 at the moment? Oops, what happened there? Right, why am I not typing anywhere? Delete that. Right, I've got the control button hit, so let's just get... Right, my control button was depressed. Let's do a plus back there. Right, so we're going to go to 10 to the 10. I'll run these quickly, because if it works 10 to the 10, we'll see. And this one's 10 to the 10, right? And we'll go back up here, and we're not even going to call this... we're not calling that our calc time. Or are we? We're calling it... We could call it... We'll call it the sum time. Or collect. It's our collect time, because we're collecting everything back. So, and that's T6. No, sorry, I've got to take that back. That is T6, T2. Yeah, that's our collection time. Yeah, it's that little. It's the cost of this. That's our collection time. So we're going to just run that again. This time we've increased it by an order of magnitude, and hopefully, I don't know if it would at least to be a positive sign if we see. So this is 3. We want to see our 3 increase, but we want to see this one here kind of like stay constant. And it looks like it has, because here, when we increased it, it went from 19 to 17. So I'm going to do that again. And that's probably the cost of doing it. A few seconds at the beginning and 15 or so seconds at the end. Right, why did that? Okay. So this is one reason. Unable to allocate 74.5 gigs of an array shape this. Okay, so that broke it for a start. So the single threaded one doesn't work because did we just get too big? Can we hit that F5 again? I just want to see what that error message was. Oh yeah, it just can't allocate that amount of memory. Array memory error. So unable to allocate that for data type int64. Maybe we can make them smaller ints. I guess we can do a D type int or np.int. We can make it small enough, but then our integers, will our integers hold those big numbers? So possibly run out of memory for that, funnily enough. That's an interesting one. Okay, well that's one good reason, but I think the multiprocessing will also fail for the same reason, because the multiprocessing one initially has to do the same NumPy array. So even if I was to comment out the single-threaded version and no multiprocessing, I'm still going to get that error message by doing the 10 to the 9 over there, or 10 to the 10, I think it was. Yeah, it does. It comes up with the same thing. I'm unable to allocate this amount of memory. So, okay, Can't do a test at something bigger. Would maybe need to do it in a different way. Um, Possibly the alternative is really, if you wanted to see a gain, I guess, is to. I'm a bit surprised. Well, maybe NumPy. Because what's actually happening, the thing about NumPy is what's actually happening compared to maybe if you did it on the fly, you have to think of other techniques, is it allocates this contiguous block of memory. That's why NumPy is faster than lists. Lists will split it all over the place. Um, Lists is actually bigger in memory, but it will allocate a continuous block of memory. But I'm surprised you can't just do a 10 to the 10, but that's because it's like 1, 2, there's 10 to the 10 numbers. Like single numbers continuously in memory. So there probably is a way to do it like that. But the alternative to that really the alternative to that is to go and let's just think is to make the function or what we're doing more complex. So in a moment, the original question was, let's just add up numbers. Now, you're not going to get this great gain on adding up numbers, I guess, anyway, because it's a simple process. But maybe if we went back down to, and I can try and do this, we'll go down to 10 to the 9, but we won't just add up numbers, but we'll do something like the square of numbers or something like that. We'll do a little process on it. So here, and it's actually quite useful, I think, because this was a sum array. But instead of doing the sum array, let's just do this is np dot array. I just wonder if we can do something like maybe even a for loop. For I in array. That should be good enough because that will be slower. And then we're going to sort of get some sort of result there. So we could do results equals. So we'll initialize result at 0. So we just say result equals 0 to start with, and then we'll say something like result is I squared plus 3. There we go. And we'll do a plus equals because we're going to increment the result. So we're going to get back a number. Now it's not going to be any more the sum of numbers, it's going to be a result. So we'll return back this result. And what comes back here is going to be this actual whole result, whereas here we're going to split it into 4 bits, and then we're going to loop through them, and we're going to now, okay, fine, the looping is going to start back because we're going to, when we get this array, it's going to start from index 0. So the answers will be slightly different. Will actually be massively different, not slightly different. There'll be massively different answers. So I'm just going to run that anyway. So hit F5 to run it. And well, funnily enough, that still took 2 seconds. And we still see that, like, the bulk of the work in the hold on, where's our first one actually? Right. Control CCC, comment, get out of that. That's going absolutely mental. Right. Never had that before. Stop that process altogether. Right. What happened there? Um, 10 to the 9, np.arrange. We did our sum array, but this time it went in on the sum array. So we created an array. We passed an array into here, an NumPy array. We passed it into here, and then we did we initialized result to 0, and then we said that result equals right. I'm just wondering, that should have been fine. I'm just wondering why that threw an error message. It worked on the hold on one sec, let's just go back up here. Right, that was a no multiprocessing one. Let's just run this separately then. F5, no multiprocessing. Runtime warning, overflow encountered in scalar add. Okay. I'll hit stop again because I obviously can't do this, so I've got to be very careful about that. But that would throw the same error. I'm just going to remove the squared for a second and just try and do the same thing again. There should be nothing wrong with this in particular. But I'm getting an error message there. Probably, is it because we're using NumPy arrays? I'm averse to just saying runtime overflow encountered in scalar add, result equals result. But why can't you do that? You can't add up to I'm just going to check this out on one of the chats. So I'm just having a look here. Let's see what it says. Warning about overflow encountered in scalar indicates that you are exceeding the maximum value for the integer data type being used, resulting in an overflow. Okay, that's why. 64-bit integer, because it's right. I wonder if I take the time down, the size down to 7, and if I was to do the time, then I'd have to take that down to 7 over here. And well, that would be a good sign anyway. So if I hit F5, I wonder if that's going to work. You get negative numbers and I get this horrible runtime warning error. So this is a problem with taking any coding language to a limit. Actually, you've got to be careful about these things. I'm actually thinking that it's not the error over here, but basically what's happening is totally equal sum array, but sum array is actually just this. Right, I just can't handle it. Right, okay, so I'll do something like this, which will reduce the size, which is if, and increase the complexity as well. But so if I percentage 2 is 0, then result equal plus I, and then otherwise else result. I can do the plus equals now, but I'll just do equals result minus I. There we go. Just try something like that. So and I'll add on an I squared and take off an I squared. I don't know. Maybe that should I squared, and over here I squared. There we go. So hopefully adding a square number and taking away a square number won't be so disastrous, because they'll like sort of like zigzag around. Because basically I'm hoping that I sort of get something like that, but the net effect of that is, you know, hopefully something like that basically. So let's try it out anyway, we'll see. And I'm not sure because the numbers are just going to get sequentially bigger. So let's see. It might not like it still. Yeah, it doesn't like it. Okay. Let's just go with smaller numbers then, which is, I won't even do that then. I'll go like 10 to the 5. There we go. Go much smaller numbers because I'm squaring these numbers now. 5. And here 5 over there. Nope, still getting interesting. So okay, it's got something to do with this. Maybe it's because I created a NumPy array and it's not liking it. Let's just go back. There are a couple of options. Okay, use NumPy unsigned 64-bit integers. The total sum of okay. Right, it's just too big for it to handle like that. But I don't want to do an efficient method. On purpose, I'm trying to do an inefficient method. So the change. Maybe it's in the declaration of the array. Well, let's have a look. We'll stick this in here, D type. And if I do that, then I have to I wonder if that's sufficient over there for the code. I've put in a D type over there. And this is of type, by the way, MP. We could type hint dot array. This is of type MP array. Position. Nice, be careful about that. How do I type hint for a NumPy array? Question mark. I just asked how I type hint for a NumPy array because I just want to make, like, you know, it gets a lot of things in place. Sometimes when you do type hinting, Okay, ND array, that's what it is, np.nd array. So, of course, I should have known that. This thing here is just a type np.nd, getting an n-dimensional ND array, so that's basically what's going in here. But anyway, that won't make a difference, it's just a type hint for things in here. So let's just run this again. I still don't think that doing the np.onside in 64, oh yeah, it does do, it works, it's fine now. So that's fine. We'll go back in time now because we've got. So let's increase our sizes back. So we'll go back to 10 to the 9 over there. I'll put a 10 to the 9 over here. We're not running our second function yet, and then we're going to try and run the second function. So hit F5 on that and run the second function, and yeah, now it's taking. I don't know how long it's going to take. Good, nice long time. Hopefully I'm not going to murder this. Maybe I shouldn't have jumped straight from 10 to the 5 to 10 to the 9. Do I have the patience to wait? It's taking a long time here. So I shall hit pause on that, or stop, because I'm not waiting that long. We'll go to 10 to the 7 again. So that's 2 orders of magnitude up. Remember that we're just at the moment just running it on the no multiprocessing one. I'll stick 10 to the 7 in the multi-prop one as well for if we do run it. And now I said if rather than when. Let's just see if this is more reasonable in time. So our processor started again. And basically in our process, so it's going through, it's much less efficient now. It's going through every element in the NumPy array, and it's making its result, and the result is I squared over here. It's just incrementing it if it's an even number by adding on I squared, or taking off I squared if it's an odd number. So it should give us something, God knows what. Still taking a long time to do. So it did 10 to the 5 quite fast. I mean, in a way, possibly, like if it ends now, it would be a good example of multi-threading, assuming that multi-threading works nicely. What I'm going to do is hit stop. I'm going to go back. 10 to the 5 was fast. Let's just check that it was fast. There we go. Yeah. So that's taken 0.78 of a second. Now I'll do 10 to the 6 then. Maybe that will take 7 seconds. Because 10 times faster. 10 times longer. So we only have to wait several seconds on that. Because the other one will be 70 seconds. And maybe that's why. So it says it's taken 7 seconds. The other one will take a minute. Maybe I need to have patience for a minute. But on this one now, I'm going to do, I'll start with 10 to the, well, I'll go straight 10 to, I'll do 10 to the 6 on it. Let's just see what happens. So we'll have 10 to the 6 on both. And worst case scenario, I'll jump out of it. So we got single threaded, which is the no multi-processing versus the multi-processing. And we're going to run that. And in 7 seconds, we'll get our first answer, because that's going to be the single threaded answer. So still to remember, we're going to get 2 different answers. Okay, what's happened there? Unsupported for int and type. I've got to put a D type in there. Right, so D type. There we go. That's what we need. And hit F5 again. This took, like, the first time around it took, well, it's basically 8 seconds because this is 7.9 and this is 8.1. So on average it's about 8 seconds. But we should, so hopefully 8 seconds is up. So we get our 8 seconds. And now we see that we've got, in order to split the arrays, it was so like a fraction of a second there. But then we've got, so this now works. This is the example of where multi-threading is better because the processor is a bit more complex than a simple addition. And it looks, this has cost us like a quarter of a second. Now, okay, there's a bit of a cheat here as well because I was doing like a square and adding a square and taking off a square, but I was starting, I did split it in 4 arrays and I was starting from much smaller numbers. So the first one would have had much bigger numbers. So really, if I was going to do these arrays, I'd have kind of like really started them, or at least made the numbers larger by the incremented values. Although, I wonder if that... So we do get the same answer for both. So we've had, now all of a sudden, we've had the gain, and we can literally add it up and we can see this gain, right? The cost of splitting was a fraction of a second. Now, I don't know why the cost of splitting was that much. Well, okay, fine, because our array size was just smaller. So the cost of splitting was much smaller for a start. But then the first process here, it sort of like attacked it really fast. And nothing really got allocated to the other 2 bits. It's almost as though this has completed it much, much faster. So that's a bit of an interesting one. I wonder if the array split was... because we just split it into 4. So that's really interesting because they're doing the same processes now. And we're adding all of the pieces up. So it's not obvious, although this is kind of like more expected, as in I was hoping to see this at the outset, which is at least with something a bit more complex. But funnily enough, I was expecting to see the simple one at least be of the same order of magnitude. But there's certainly a gain now in doing this. So this has taken us 5 seconds, basically, 5 and a bit seconds, 6 seconds. Whereas the multi-processing way, so the single-threaded way, has taken us 8 seconds. And I just wonder if I increment this time now, and I'm only going to do it in a multi-processing one. I've increased it by an order of magnitude, and I'm going to hit F5 again. The first one's going to take roughly 8 seconds, we know that already. But the question is how fast is the second process going to be? Because it's got a bigger number in there now by an order of magnitude of 10. Now, it's done all of the first bits, and it's actually used a tiny bit of the third processor. So it's done a bit more allocations, but notice the consolidation is taking a long time, which is really, really weird. Like, the consolidation is taking a huge amount of time. So that's an interesting one. It's taken 30 seconds, in fact. So that's really, really weird. Now, okay, maybe it's not weird, because, I'll take that back. Yeah, why should it have taken 30 seconds? Now, we know that this would have taken 70 seconds, at least, because if we increased that by an order of magnitude of 10, it would have gone from, like, well, 80 seconds, basically. So we're definitely getting gains, but it's non-linear and not 100% predictable. So I think I might leave it over at this point. We've seen some advantages and some disadvantages of multiprocessing, but one thing for sure is It's only really worthwhile doing this if you are going to be doing something that's relatively processor intensive, that's going to be quite heavy. And even when you do it, you have to really think about how you're splitting the processes up, from this one process, how you are splitting your processes up into the multiple processes. It doesn't have to be 4, it could be any number of them. But so like how you're allocating that, doing the computations, and then finally, the biggest piece really is actually how you join them back, because the biggest time cost every time that we've seen in multiprocessing is the get function. So it's the biggest time cost really is, I wonder if that's cost me something because I've done a total twice. That would have been a little erroneous thing over there, because I did total twice. So whatever my get was, my get would have been doubled. I wonder how much difference that makes. I'm going to run it just to see. Does that go from 31 to 15, basically? But still, continue. We've got a split. The split happened fast now. All of the components happened. We've done that. Now we're waiting for the get. But finally, it's kind of like this blue section over here was, our sort of like our biggest cost in a way. So this piece over here is our biggest, and we can still see it hanging here. So this entry piece was fast. These computation pieces were fast as well. But we are seeing that taking a long time. There we go, 39 seconds. It still took us this relatively large amount of time. So, it's way more than 10x, right? It could be 100x, but I'll give it a 10x down there. This is 10x over there in terms of time, sort of like getting it. And I don't know why yet. I can inspect, so like I can ask the question, but something like, why does res.get take so long? Question mark. It should know what res.get is from our context. So let me remove all of the things over there and zoom in, Control plus a few times to there we go, so that we can read it a bit better. So I've asked why does the res.get call in the multi-process example is likely taking a long time because it is blocking, okay, until the result is ready from the worker process. Almost like it's waiting for the slowest worker, but okay. So all of these times are fictitious times because they're all just, the worker started in a fraction of a second, the worker started in a fraction of a second, the worker started in a fraction, the worker started in a fraction of a second, but he's waiting for the one of the workers to complete, or at least the last worker to complete. So the last worker, well, it took 39 seconds for the last worker. Now that is a gain actually, if that's the case. That's fine. We actually quite like that. So the res.get, that's a good thing, because what it's then saying it's doing is it's actually splitting. So it's splitting this into its constituent pieces, and each of these is taking a certain amount of time. One might be quicker, one might be slower. So they're all taking their lengths of time. And it's basically saying wait till the last, well, the res.get is waiting until the last one's finished. And the last one here was 39 seconds. It was like this one. Now, what we do know is on the single threaded one is we got the same thing, and it goes to its process. But we know that its process, we can estimate the process because I can't be bothered to wait for it. But basically it's like 70 seconds So the single thread, I'll call it ST for single thread, is taking, like, clearly now it's working the way that it should. It's taking multiple times compared to the multi-thread. So finally, we show that the multi-thread is better, but not in all cases. We've got to be careful. If this allocation process is longer and the collection process at the end is longer, or one of the threads is occupying a lot of time for some reason that we don't know about because we haven't done the allocations right, then all of a sudden the multi-thread might actually take longer than the single thread. Although we should believe that for any kind of like largest process, so long as we're splitting it up into like constituent bits, that the multi-thread will actually be quicker on average. It's going to use more cores. Hopefully, if you're using the cores properly, and it will do it, and then it will combine them and give our bits at the end. So that's pretty much it. That's the multi-threading in Python. It was a bit longer than I expected this little clip-it video to go on for, but yeah, that's it. Multi-threading in Python. If you like this, hit the thumbs up button. If you also follow, subscribe, and all the rest of it. Even if you don't like it, still hit the thumbs up button, follow, subscribe, and all the rest of it too. And finally, if you have any comments, certainly leave comments in there. It'd be interesting to see what other people say about the multi-threading versus single-threaded process, or multi-threading in Python, so versus regular Python. So that's about it, and I'm signing off.